Good morning, everyone. So welcome to my YouTube channel, Subgroup. So today we are going to see for the lecture on characteristics of group. So let's see today's result. We are going to prove a very important result that if H is unique subgroup of given index, then H is characteristic subgroup of. So I'm writing that result. If H is a unique subgroup H is unique subgroup if H is unique subgroup of a given index of group G, then H is characteristic subgroup of G. So let's see its proof. So let index of H, let H is unique, let H be unique subgroup of index N. Okay. Then what is the meaning of it? Means that the number of left cosets of H in G equal to the number of the number of right cosets of H in G is equal to N. The meaning of index is number of left cosets of H in G is H, and that is also equal to number of right cosets. Number of left and right cosets are always equal, and that is equal to 1. Okay. So I am taking on the left cosets. Okay. So let HA1, HA2 up to HAN be distinct N cosets, right cosets be right coset of H in G. Okay. So these are the right cosets such that the distinct right cosets, the N distinct right cosets of H in G. So the index of H in G is N, and these are the distinct right cosets. So it means we know that the union of all the cosets is nothing but H, and the union of distinct cosets is nothing but G, and they are the distinct. Either two cosets are equal or they are disjoint. Okay. So G is equal to HA1 union HA2. So here what are A1, A2? A1, A2 up to A and R in G. Okay. HAN. Okay. Here and HAI intersection HAJ is equal to 5, 4, 1, I and J, I not equal to 2. Okay. So we can write this union as I goes to 1 to N HAI. Okay. So let phi be an isomorphism of G. So put K is equal to phi H and Bi is equal to phi AI for I less than equal to greater than equal to 1 and less than equal to 1. Then K is subgroup of G because image of a subgroup is a subgroup under an isomorphism. Okay. So this is subgroup. Okay. Now G is equal to union I goes to 1 to N HAI. So this implies phi G is equal to union I goes to 1 to N phi HAI Then what is this? This is nothing but I goes to 1 to n phi h phi ai. Okay. So this is equal to I goes to 1 to n k bi. Okay. K bi. Okay. We claim that index of K in G is also n. So for that, we have to show that it means G is equal to union I goes to 1 K B I and K B1 K B2 up to K B N are disjoint. Okay. Are pairwise disjoint. Disjoint means pairwise disjoint. Are pairwise disjoint. Pairwise disjoint. Okay. What is the meaning of pairwise disjoint? It means that KBI intersection KBJ is equal to phi for I and J less than equal to I and J less than equal to N and greater than equal to 1. I not equal to J. Okay. The meaning is this. Okay. So we will prove it by contradiction. If possible, suppose that. So this fact already proved. So what is this? So first we have to show. We know that phi is an isomorphism. Phi is an isomorphism. Therefore, G is equal to phi G and phi G is nothing but union KBI. Okay. So this implies G is nothing but union I goes to 1 to N KBI. Okay. So this fact is proved. Now we have to show that they are disjoint. If possible, suppose that KBI intersection KBJ is equal to not equal to phi for some I j. Okay. Then there exists K1 belongs to K1, K2 belongs to K, such that K1 Bi is equal to K2 Bj. Okay. Since K is equal to phi G, so K is equal to phi H, implies there exists H1, H2 belongs to H, such that K1 is equal to phi H1 and K2 is equal to phi H2. Okay. Now, K1 Bi, K2 K2 Bj. So put the value of K1, K2, that is phi H1, and what is the value of Bi, that is phi Ai, that is K2 value is phi H2, and what is the value of Bj? Phi Aj. Okay. So, and we know that phi is homomorphism. By property of homomorphism, what we can write this? So, by property of homomorphism, what is this? Phi, okay, and what is this? So, but phi is 1, 1. So, this implies H1 Ai is equal to H2 Aj. Because phi is 1, 1. So, this implies H1 Ai is equal to okay, is equal to H2 Aj. Okay. Now we know that we can write it H1 Ai is equal to H2 Aj. Okay. So this part will be H, and this part will be H, because we know that you take H and H, which H, for H belongs to H. Okay. So this implies Haij is not equal to phi. Okay. Not equal to phi, which is a contradiction. To the fact that because we already know that HAI intersection HAJ is empty. They are disjoint. Pairwise disjoint. You take any I and J, HAI intersection HAJ are disjoint. Okay. Therefore, as K A K therefore K A I sorry therefore B I intersection K B J is equal to 5 4 I not equal to J. Okay. So finally what we got? So finally finally we have G is equal to K B1 union K B2 union up to K B N. Okay. We have K B1 K B2 up to K B N are pairwise disjoint. Joint. So pairwise disjoint. So what is the meaning of this statement? The right cosets or the union of right cosets of G is union of right cosets of K in G is G, and these cosets are disjoint. So what does it mean? It means that index of K in G is N. Okay, but H is unique subgroup of index N, but H is unique subgroup of index N. Therefore, H and K has to be equal because H is unique. Therefore, H is equal to K. So this implies H is equal to phi H because H is nothing but phi H. So we have phi H is equal to H for any isomorphism of G. So this implies H is characteristic subgroup of G. So this implies H is characteristic subgroup of G. Okay. So today's theorem is true. If you have any subgroup, a unique subgroup of a given index, then such group is characteristic subgroup. So we have shown this. From this is very important results. Okay. So today's lecture up to this. If you have any problem related to this, you can comment on my section. Like, share, comment, and subscribe. Thank you very much for today. Thank you very much.